Okay, good evening and welcome to your AP Stats Notes Online. Tonight we're going to talk about density curves a little bit more, but in particular about a specific type of density curve that we're going to carry through all the way out until May. So it's hugely important, this idea of what's called a normal distribution. Okay? So anyway, I know that for the last set of notes, we talked a lot about density curves. And so again, the idea is when you collect your data, we're going to go through this sort of step-by-step process on what to do with that, right? So we're going to plot it, whether through a box plot, dot plot, stem plot, histogram, whatever. Look at the overall pattern. We talked about SOCs, right? And then we want to calculate some numerical summaries so we kind of get a more specific idea about what the data is trying to tell us. Now, as I said before, sometimes the pattern is so regular that we can sort of sketch out a smooth curve from it. And so an example of that, and we did one in the notes before, but this histogram shown here is for ACT scores for a sample of students in a large high school. It's fairly regular kind of distribution, and so we could kind of fit a density curve over this guy that might look something like this. And you want to try to capture those tops of those boxes the best you can, but something like that. And again, the idea is to take these bars away, and all you'd have left is that curve. And so, we did talk about before about the disadvantage to histograms is that you sort of lose those individuals in the histograms. Dot plots, stem plots. You can see all the individuals in the distribution, the data values for those individuals in the distribution. Histograms, you lose that a little bit. Well, now we're going to take the bars out, and we even lose more accuracy and specificity, I guess, when we start talking about density curves. But again, the idea with the density curve is just to get a general idea of what that distribution looks like. Okay? So anyway, that's, again, the idea behind a density curve. We have properties of a density curve. It's got to be all on or above the horizontal axis. We talked about that before. In the entire area, if you look back at your curve, the idea behind the curve is that it captures all of your individuals the best that it can. So the area under that curve needs to be equal to 1. And since we're talking about the area under the curve, then that's how we're going to figure out what proportion of individuals. So the area under this entire curve, the proportion of individuals under that curve is 100%, and so the area is 1. Well, if we want to start talking about what proportion of individuals are in certain intervals, so say from, I don't know what this is, maybe 19, who scored from a 19 to a, I don't know, what is that, 22, on the ACT, then you'd have to find the area under that curve. And we talked a little bit about, certain density curves. Remember, there's different types of density curves. We've got uniform density curves. We've got skewed density curves, and then symmetric and things like that. For uniform, it's easy. You just find the area of a rectangle, right? But when there's an actual curve involved, we got to get a little bit higher order math going on, and definitely higher order than what we want to talk about. So, but anyway, that's why we're going to keep talking about area under the density curve, because it lets us know what proportion of individuals are in certain intervals. Okay, and we'll discuss why they have to be intervals later. All right, so just some quick review again. Shape, mean, and median. You got 3 density curves right here, one that's right skewed, one that's symmetric, one that's left skewed. I'll give you a couple of seconds and see if you can't locate the mean and the median of all 3 of those. And you'd want to be able to talk about why you chose the places that you did. But go ahead and plot those out. I'll give you a couple of seconds. If you want to start the video, you can. and then start it back up, and I'll show you where they should be. All right, you got them? So for a right skewed distribution, your median is probably going to be about right there. Your mean should be to the left or the right of that? Yeah, it should be to the right, right? Since we're skewed right, it should be to the right. Symmetric, we talked about symmetric. Mean and median should be the exact same in a symmetric distribution. So your median is going to be here, and your mean is going to be here. And again, we use mu to talk about the mean of a density curve. And we'll also use sigma for the standard deviation. We'll talk about that in a minute. So in the left skewed, it's going to be kind of the opposite as the right skewed, right? Your median might be somewhere right here, where your mean is going to be to the left of it. So about there. Okay? All right. Good. Well, a little bit of a review about density curves, but what we want to talk about tonight, mainly, is an important class of density curves. It's called the normal distribution or the normal curve. And in order for a density curve to be considered normal, there are some characteristics that the density curve has to maintain. It has to be symmetric, it has to be single-peaked, and it needs to be bell-shaped. So your bell curve. Probably not the first time you've ever heard of a bell curve, or the first time you may have talked about a bell curve, but that's what we mean. If a density curve is going to fit into basically a bell curve, then it's what we call a normal curve, or a normal, your distribution is normally distributed. Okay? All normal distributions have the same overall shape. What sets one normal distribution apart from another is its mean and standard deviation. Okay? So what you'll do is sometimes you'll see some notation here. If a distribution is normally distributed, then you might be given the information in a format like this, where N stands for normal, and then in your parentheses, we'll list the mean and the standard deviation for that particular curve. Okay? And so, again, a little bit of detail about the normal curve. What sets one curve apart from the other is, one, the mean, right, where the center of that bell-shaped curve is. So if you can imagine that, if we were to plot all normal curves on the same horizontal axis, then those curves would move left and right, depending on where the mean is. So you've got three examples here where the mean of this curve is smaller than the mean of this normal curve, which is smaller than the mean of this curve maybe, or maybe these two curves have the same mean. And then the height of the peak would technically change based on your standard deviation. Now remember, it's a density curve, and so the total area under that curve still has to be 1. 100% of the observations still need to be under this curve. So if a standard deviation is going to be smaller, in other words, if your individuals are going to be less spread out, then the peak of that curve would have to be taller in order to fit all those guys in there, right? And so vice versa, if your standard deviation is larger, there's going to be more variability. Your individuals are going to be more spread out. Then your curve would sort of flatten out because you don't need as many individuals in the center. You've got more room out here in what we'll call the tails to accommodate 100% of the data, right? So we won't necessarily discuss a lot about how tall a normal curve is or how flat a normal curve is. Just something to keep in mind, and how we distinguish one normal curve from the next, okay? And again, all normal curves are going to have the same overall shape. Just where they're positioned on a number line would change based on mean and standard deviation. Okay, with that in mind too, again, they all are going to obey a pretty common rule. And there's something called the empirical rule, or the 68, 95, 99.7 rule. And if you can get really good at this empirical rule and using the empirical rule and recognizing when you can use the empirical rule, then life with a normal curve becomes a lot easier, okay? And your calculations become a lot shorter. And we'll talk about why as we go through this. But the empirical rule basically says this. It says that in a normal curve, 68% of the observations fall within one standard deviation of the mean. Okay, now that's not exact. That's going to be an approximation. About 68% are going to fall within one standard deviation of the mean. Okay, 95% of the observations are going to fall within two standard deviations of the mean. And then 99.7% of the observations will fall within three standard deviations of the mean. And so we give sort of an interval here. And if we go back up to these guys, so what we're talking about, if this is your mean, then your first standard deviation above or below the mean, that's going to house 68% of your individuals or 68% of your observations. Okay? And then we keep going out from there. And actually, we have a curve down here that we can use to sketch that out. Okay? So on this big curve here, so if this is our mean, and then this is our standard deviation, and this is normal, this is most of the time how we would sketch out a normal curve. You've got to show the mean, and you've got to let everyone know what the standard deviation is. And there's about 2 or 3 different ways you can do that. For right now, it's going to be really helpful if we actually take the numbers for the mean and then show the tick marks for the standard deviation. So the standard deviation might be about right here. The first standard deviation is typically about 2/3 up this curve. If you're thinking about walking up this hill, about 2/3 of the way up this hill is where you're going to find your first standard deviation. If you're reading the book, and hopefully you are, the book talks about sort of this inflection point, this change in inflection. Again, that's sort of a nod towards calculus. It's where the graph goes from increasing to decreasing. But again, if you haven't had calculus or don't remember or don't care, then that doesn't make a lot of sense. But so about 2/3 up the curve is going to be your first standard deviation. So below the mean, you'd be here at mu minus sigma, and then here at mu plus sigma is one standard deviation above the mean. And then, out here about maybe 1/3 up the curve is your second standard deviation, so mu plus 2 times sigma. Oh wait, that'd be a minus, because that's below, right? And then this guy over here, mu plus 2 sigma, again about 1/3 of the way up the hill, 2/3 of the way down the hill, however you want to look at it. And then out in this tail is where your third standard deviation is going to be. Now in a normal distribution, again, 99.7% of the observations are going to fall within these standard deviation marks here, 3 standard deviations away from the mean. Okay? So let's do some segmenting of this normal graph, okay, of this normal curve. So let me ask you some stuff. In here, in this area right here, what proportion of your individuals are in the middle right there? Well, it's within the first standard deviation, and so hopefully you're saying 68%. Okay? Okay, good. Now, what if we change colors here, and we start talking about, let's go this way. Okay, so from here all the way out to here, what proportion of observations are within 2 standard deviations? Well, that's 95%. Okay? And then from here all the way out, let's see, let's do this. We don't need the color, we've got red here. all the way out here, that's where 99.7% of your observations are sitting. And so these colors might actually get in the way here. So I wonder if we could do something like this and make more sense of it. Hope you're doing this in pencil. So from here to here is 68%. And then from here to here is 95%. So we can get rid of this. And then from here all the way out to here is your 99.7%. Now, let's play a little bit of a game here. Just kind of getting a sense of this curve here, right? It's symmetric. It's bell-shaped. We have this empirical rule. And so let's play a little bit of a game here. What if I asked you what proportion of individuals are sitting right here? Let you think about it for a second. Well, since it's symmetric and there's 68 within one standard deviation, then one standard deviation above the mean would be 34%, right? Half of that, which means that 34% are going to sit over here. Okay? Let me ask you this. So we've got, well, let's do this. There's 34% in here, 34% in here. What about just in here? Just in here, right? And in here. These are the next two areas I want to talk about. If we're going to take this in pieces, okay? Well, I know that there's 95% in this entire interval, 2 standard deviations away. 68% of the observations are within 1 standard deviation. So what's the difference there? 95 minus 68 gets you 27%, right? So then what proportion of observations are sitting right here? Well, again, it's symmetric. This curve is symmetric, so I have to have equal number of observations here and here. So in these two areas, I've got to have a total of 27%, which means that in just this guy right here, I've got 13.5%. And in just this area right here, I've got 0.5%. Okay? Now let's keep going out in these pieces, right? What about right here and in here? What proportion of observations are in those two areas? Well, again, we've got 95% of our observations within 2 standard deviations, and we've got 99.7 within 3 standard deviations. So if I subtract those, I get 4.7%, and that tells me the total proportion of individuals or observations that should be sitting in these two intervals. Well, if the total is 4.7%, then half of that, or 2.35%, will be right here. 2.35% will be right here, for a total of 4.7. Okay? All right. Last but not least, we can talk about what proportion of individuals are out in these tails each, right? Well, again, the entire curve is 100%. We know that within 3 standard deviations, there's 99.7%, so that difference is 0.3%. So all the way out here, you're going to find 0.15% of your individuals, and all the way up here, you're going to find 0.15% of your individuals. That's less than a quarter of a single solitary percent, so not a lot. You're not going to find very many observations outside of 3 standard deviations, okay? But that's how you sort of break down the pieces of this curve, and as long as we're talking about standard deviations being on a standard deviation away from the mean, then we can talk about the proportion of individuals that are within these certain intervals, right? So for example, suppose the ACT scores are normally distributed with a mean of 23 and a standard deviation of 3 points. Well, that means we're going to change some of this stuff, right? So if I were to sketch this curve, okay, if I were to sketch this normal curve, then I would draw the best bell-shaped symmetric curve I possibly could. And you're going to be pretty terrible at it at first. I'm still not really good at it, but who cares? It's not an art class, it's a math class, so it doesn't need to be perfect, but just do your best. So that means that right here in the center is going to be 23. And then at the first standard deviation, you're going to have 26 and 20. And then at your second standard deviation, your scores are going to be 29 and 17. And then your third standard deviations are going to be at 32 and 14. Okay? So we can talk about what proportion of test takers score in certain intervals. Well, if we want to talk about between 20 and 26, well, that's the first standard deviation above and below the mean. The proportion of individuals that are following this interval is, from our empirical rule, 68%. Right? What proportion scored between 23 and 26? Well, here's 23. It's your mean. 26 is at one standard deviation. I only want the right side of this first standard deviation, so I want half of 68, or 34%. What proportion scored between 17 and 20? Well, here's 17, here's 20, right? It's this area that is within 2 standard deviations, right? But I don't want this middle part, which is 68%. So that means that in this area and in this area, I've got 27%. And I don't even want the upper interval. I just want the lower interval. So I'm going to divide my 27% in half and get 13.5. So 13.5% of the individuals are in this interval. What proportion scored above 29? Well, here's 29. Above 29 takes me out here. I'm outside of my second standard deviation, where 95% of those individuals sit. So that means that with the combination of this guy and this guy, I've got my remaining 5%, right? But I only want the top half, right? So I need half of 5%, which is 2.5%. So 2.5% is one way to do this. Now, if you've got these intervals broken out, then above 29 gets me my 2.35% with this area, and then 0.15% with this area, and you add those two, and you're going to get 2.5%. So there's a couple different ways to go through these calculations. What proportion scored below a 14? Well, 14's over here. Below a 14 puts me all the way out in this tail, and so we're outside of 3 standard deviations. If we were inside of 3 standard deviations, we'd be at 99.7%, but we're not, we're outside. And so outside 3 standard deviations is 100 minus 99.7, which is 0.3%. But then I only want to be less than, and so half of 0.3% is 0.15%, which again is exactly what we have written above this interval from what we were doing before. So we've got 0.15% of all ACT test takers scored below a 14, right? So what did you score on the ACT if you took it? And if you did take it and you remember what you scored, can you kind of see what proportion of test takers scored higher than you or lower than you? That all depends on if you fall on one of these standard deviations or not. Okay? The next question here says, what proportion scored below 21? Well, 21 is like right here, right? It's not on one of our standard deviations, and so it becomes a little bit more complicated in terms of how we want to find the proportion of individuals that score below that, to find that area under that curve. So why don't we worry about that at a later time, okay? So for now, we'll stick to just these just these standard deviations and the proportions in relationship to those standard deviations, okay? So use your notes. This will help you some. I'll give you a couple of problems. There should be some check your understanding problems in your book. And there is indeed one on page 114. There's a check your understanding. So take a couple minutes, see if you can't scratch out those answers. If you want to do it here somewhere on the back page of your notes or somewhere, just kind of scratch it out, and then we'll go through those really quickly tomorrow when we're in class, and then we'll get to any questions from the notes or questions from the homework. Don't forget, quiz tomorrow on percentiles, z-scores, so on and so forth, etc. All right? Have a good night. See you guys tomorrow.